Welcome to Biogas Basics. My name is Jürgen Kubel, and this is the sixth part of the mini-series about the gas system of biogas plants. This presentation explains pressure relief valves, or PRV, and the gas safety chain. A pressure relief valve is the last resort that protects a tank against over-pressurization and potential structural damage. A PRV should never activate, and yet it is one of the most common sources for methane emissions on AD plants. Often this is not the fault of the PRV, but of the underestimation of the pressure gradient on a biogas plant or mismanagement of gas storages. But PRV themselves can also contribute to methane emissions. Let's find out how to size them correctly. We start with the terminology. The set pressure is the pressure at which the PRV opens, or more precisely the pressure at which the PRV starts to control the flow. The overpressure is the pressure at which the PRV has the full lift and vents the design flow. The ratio of overpressure to set pressure is an important quality criterion of pressure relief valves. Good valves achieve full flow at 110% of the set pressure. Don't accept valves with a higher pressure drop. The pressure drop is very critical in low pressure applications like biogas plants. After the PRV opens, it closes again when the pressure drops below the closing pressure or reseating pressure. A good PRV closes at 95% of the set pressure. Let's look at an example. A digester has a gas dome with a maximal allowable working pressure, MAWP, of 7 millibar. Exceeding this pressure can lead to irreversible structural damage. The design pressure is 5 millibar. This is the pressure that is expected in normal operation. The set pressure of the PRV is 5.5 millibar. If the outlet of the gas dome is closed, for example, because the gas consumer stops, gas will accumulate in the gas dome. Eventually it will be filled, and the pressure will start to rise. When the pressure reaches 5.5 millibar, the PRV will open. At 6.1 millibar, the PRV will be fully open, and all the gas production flows out of the PRV into the environment. If the biogas flow to the gas consumer recommences, the pressure in the gas dome will drop and then the level will decrease. Eventually, the gas dome operates again at the design pressure of 5 millibar. When the pressure drops below 5.2 millibar, the PRV closes. PRVs come in different embodiments. The most common pressure relief valve is the hydraulic pressure relief valve. It comprises two chambers separated by an inverted weir. It is filled with a barrier fluid, which is almost always water with an antifreeze agent. One section of the PRV is connected to the biogas space, the other to ambient air. In normal operation, the level difference between the two sections is the water column of the headspace biogas pressure. When the tank experiences overpressure, the level in the biogas chamber drops until it reaches the weir, at which point the gas forms bubbles that flow through the barrier fluid. Once the bubbles reach the surface, the biogas escapes into the environment. If the tank experiences a vacuum, the process reverses. The level in the airspace is pressed down until it reaches the weir. Air bubbles through the barrier fluid and enters the biogas space. At full flow, the pressure drop of the PRV is the hydraulic pressure difference plus the pressure drop of the two-phase bubble flow. Even though this type of PRV is very common, it has many disadvantages. The relief pressure is defined by the geometry and the level of barrier fluid in the chambers. The set pressures for overpressure and underpressure are linked through areas in the two chambers. The two-phase flow has a very high pressure drop. When a hydraulic PRV vents, the barrier fluid is sloshing around in the PRV, creating a high pressure drop and pressure oscillations. The biogas entering the PRV is water vapor saturated and the PRV is typically colder than the digester. This leads to condensation of the water vapor. The condensate fills the PRV before it flows out through designated condensate outlets. The condensate will eventually dilute the antifreeze agent. If the antifreeze is not topped up regularly, the PRV can freeze in winter and lose its functionality. A hydraulic PRV is maintenance intensive and requires working platforms as it must be accessed frequently. The only advantage is that it is a simple system from an ATEX perspective, and only one system is required for both over and under pressure. The picture on the left side shows a hydraulic PRV. Hydraulic mechanic pressure relief valves have separate chambers for over and under pressure. They comprise a lid that swims in a barrier fluid. The weight of the lid can be chosen to select the set pressures for the pressure and vacuum relief valves individually. In an overpressure event, the lid lifts partially out of the barrier fluid, but biogas must still flow as a bubble flow through the barrier fluid until the lid lifts completely. The vacuum side uses the same principle. Compared to the hydraulic PRV, the hydraulic mechanic PRV suffers less from condensate ingress. The set pressures for PRV and VRV can be selected individually. The mechanic hydraulic PRV still has a high pressure drop when activated because of the bubble flow. The fluid oscillates in the PRV and causes pressure spikes. Compared to a purely hydraulic PRV, two separate systems are required, one for overpressure and the other for vacuum. Mechanic pressure relief valves have a weighted lid that lies on a seal. Once the pressure overcomes the gravitational force of the lid, it will lift and gas flows out. A separate chamber provides protection against vacuum using the same mechanism. Compared to the two other PRV systems, a mechanical PRV provides many advantages. The set pressures can be adjusted individually. The PRV has a very low pressure drop. Its overpressure is not far apart from the set pressure. Once the PRV lifts, the flow and pressure are constant and do not oscillate. A mechanical PRV has low maintenance requirements and a low leakage rate. It can be equipped with a proximity sensor to detect venting and raise an alarm on the SCADA system. The disadvantages are that two separate systems are required for over and under pressure protection. A mechanical PRV is also prone to sulfur buildup on the inside of the valve. The lid must be lifted occasionally to prevent it from getting stuck. This slide compares the three types of PRV. The PRV were overpressurized and the pressure was measured over time. On the left side, we see the hydraulic PRV. The overpressure is 3 millibar. Once activated, the pressure spikes to 5 millibar before it drops off. After 50 seconds, the water column in the PRV starts to oscillate. From an engineering standpoint, oscillations are always bad. If the flow through the PRV reaches a certain value, so that the water column is excited at its eigenfrequency, a resonance disaster can happen which can lead to a blowout of the barrier fluid or high pressure drops. The hydraulic mechanic PRV has an overpressure of 4 millibar. It also shows pressure fluctuations, though no oscillations in this figure. The pressure variations are around 2 millibar in both the hydraulic and hydraulic mechanic PRV. 2 millibar are 50 and 67% of the overpressure respectively, and in both cases, the pressure increases above the overpressure. The last figure shows a mechanical PRV. The set pressure is 6 millibar, and in this example, the overpressure is 17 millibar. The ratio of set and overpressure is quite large in this example. After 50 seconds, the PRV opens and the pressure reaches 6 millibar. Then the flow is increased and the pressure reaches around 14 millibar. The pressure stays constant until the flow stops. This comparison shows why hydraulic or mechanic hydraulic PRV should no longer be installed on new build AD sites. The pressure fluctuations and high pressure drop make them inferior to mechanical PRV. They are not even cheaper than mechanical PRV. One of the reasons why they are still very common on biogas plants is that they can be manufactured in-house by some AD technology providers. A simple metal workshop can cobble together a hydraulic PRV, whereas mechanical PRV are manufactured by specialist third-party companies. Here's a diagram showing the pressure drop as a function of flow for a DN 200 or 8-inch PRV with a set pressure of 2.4 millibar. The pressure in the hydraulic PRV increases to 4 millibar at a flow of 300 cubic meters per hour. The pressure in the hydraulic mechanic PRV increases to around 3.3 millibar at around 750 cubic meters per hour. The pressure in the mechanical PRV stays constant for a flow of 0 to 550 cubic meters per hour. After that, it starts to increase linearly to 5 millibar at 1000 cubic meters per hour. The mechanic PRV allows higher flows at lower pressures. This picture shows a combined mechanical pressure and vacuum relief valve. The PRV is equipped with a proximity sensor that detects when the lid moves. The operators get an alarm on the SCADA system, and the venting is registered in the Historian software. In this example, the installation of the sensor helped spotting a condensate blockage of the flare line. The plant started to vent after the flare operated for a couple of minutes, because the condensate removal system of the flare did not work. Without the proximity sensor, this fault would have gone undetected. Now I want to explain the method behind selecting the correct set pressures and flows for PRV. I use an example biogas plant with 3 tanks. The primary digester makes 850 norm cubic meters per hour and has a concrete roof. It has a maximum allowable operating pressure of 20 millibar. The gas flows from there to the secondary digester, which is equipped with a gas roof with a maximal allowable operating pressure of 7 millibar. The secondary digester makes 150 norm cubic meters per hour biogas. From there, the biogas flows to the storage tank, which creates another 50 norm cubic meters per hour biogas. It is identical to the secondary digester and has the same maximal allowable pressure of 7 millibar. During normal operation, the pressure in the secondary digester is controlled to 5 millibar. The pressure in the primary digester is 8 millibar, and the pressure in the storage tank is 4 millibar. The pressure drop between the primary and secondary digester is 3 millibar. The pressure drop between the secondary digester and storage tank is 1 millibar. Every gas connection pipe has a flap. We can close the first flap at the outlet of the primary digester. The gas from the primary digester has nowhere to go but will vent through the PRV. The full gas production of 800 norm cubic meters, which is equivalent to 1040 cubic meters, humid biogas under operational conditions, will flow through the vent. 1040 cubic meters per hour is the design flow of the PRV on the primary digester. We select the set pressure to 17 millibar. The overpressure is 110% of the set pressure, or 18.7 millibar. The tank stays below its maximal allowable operation pressure of 20 millibar. We could have selected a lower set pressure, but it makes sense to select the set pressure as high as possible. The higher the set pressure, the smaller the PRV will become. A high pressure difference between the set and design pressure will also minimize the leak rate of the PRV. Now we open the flap at the primary digester and close the flap at the outlet of the secondary digester. The PRV of the secondary digester will vent the biogas production of the primary digester and secondary digester, in totaling 950 norm cubic meters, or 1235 cubic meters per hour. We select the set pressure of the PRV on the secondary digester to 5.5 millibar. Its overpressure is 6.1 millibar. The secondary digester will operate at this pressure when it is venting. The pressure in the primary digester will increase to 9.1 millibar. It will still be 3 millibar above the pressure of the secondary digester, but the pressure is not high enough to open the PRV at the primary digester. The full flow comes out of the PRV at the secondary digester. Its design flow is 1235 cubic meters per hour. Now we open the flap at the outlet of the secondary digester and close the flap at the storage tank. We chose the same set pressure for the storage tank, 5.5 millibar, and designed the PRV for the full flow of the plant, 1000 norm cubic meters, or 1300 cubic meters per hour. I will explain why in a minute. Both the secondary digester and the storage tank will vent. The flow between the secondary digester and the storage tank decreases slightly, from 950 to 350 norm cubic meters per hour. This means that the pressure difference between the secondary digester and the storage tank drops as well. The PRV in both tanks are partially open, and because of the slightly higher pressure in the secondary digester, it will vent a bit more. The PRV working at the lowest pressures and highest flows will be the most expensive. So why do we design the PRV at the storage tank for the full flow? The plant should have a ring system and a gas pipe between the primary digester and storage tank as well. And in this case, it can happen that the secondary digester is taken offline and the full gas production flows from the primary digester to the storage tank, which must be able to vent the full gas production of the plant on its own. When designing the PRV for a biogas plant, each operational case must be assessed individually to ensure that the PRV are designed for the correct flow and pressure. We talked in length about pressure relief valves, but what about vacuum relief valves, or VRVs? The truth is that these are mostly of an ornamental nature on biogas plants. The minimal set pressure of VRVs is around 1 millibar. A gas dome on top of a tank that experiences a vacuum will collapse, even if the pressure is only negative 0.1 millibar. A 30-meter diameter digester that experiences a vacuum of minus 1 millibar has the equivalent force of 7 metric tons acting on the middle column of the plant. The middle column will buckle and the roof will be destroyed. So, a VRV will not prevent a catastrophic failure. Instead, VRVs are designed as vacuum breakers on tanks with rigid roof structures. Vacuum can be caused by thermal contraction of hot gases in a tank that has been decommissioned, especially if the gases are humid and condense. Pumps that remove fluid from smaller tanks can also create a vacuum in the headspace. In the worst-case scenario, the vacuum is created by the gas consumers sucking the nominal gas flow out of a tank that has no gas production. This scenario is different from the first three. In these scenarios, the vacuum might be strong, a couple of millibar, but the volume flow is small. The VRV must be designed for a high pressure and low flow, which is a small vacuum breaker. In the latter scenario, larger amounts of air will be sucked into the biogas space, which will eventually lead to an explosive atmosphere, while the pressure will only be slightly negative. Even with a functioning VRV solution capable of operating at very low vacuums and high flows, this operation must be prevented at all costs. This is where the gas safety chain is used. The name gas safety chain originates from the time when safety functions were still hardwired into the PLC. The gas safety chain comprises a series of fail-open switches. Each switch monitors a condition that could lead to air ingress into the biogas space. These are gas dome and tank pressures. The switch opens if the pressure drops below a small positive value, for example 0.5 millibar. The gas storage levels should also be used in the gas safety chain. Gas dome levels are often difficult to measure as the inner membrane can assume many different shapes at a given filling level. Some plants use the average of 2 or 3 sensors to measure the filling level. If a sensor is damaged and shows a constant value, the average of all 3 sensors cannot drop to 0, preventing the release of the gas safety chain. For 3 sensors, a 2 out of 3 voting mechanism is recommended. If 2 out of 3 level sensors show less than 10% filling, the gas safety chain is released. If the gas dome has only 2 sensors, use 1 out of 2. Each gas dome should be linked individually into the gas safety chain. For example, a biogas plant comprising 3 digesters with 2 gas domes, each with 3 level sensors, will have 3 pressure sensors and 2 gas dome levels in 2 out of 3 configuration in the gas safety chain. The gas safety chain is part of the safety PLC, or on older plants hardwired. When it opens, all gas consumers are stopped, even the flare. Its main purpose is to prevent air being sucked into tanks, which could create an explosive atmosphere. Pressure relief valves prevent tanks from overpressurization, especially on biogas plants, which have intrinsic gas production. Closing off a tank will quickly lead to overpressure. There are different embodiments of pressure relief valves, but mechanical PRV are far superior to hydraulic or hydraulic mechanic PRV. They have no condensate problems, show a low pressure drop and even flow. Mechanic PRV have low maintenance requirements and low leakage rates. They should be equipped with proximity switches to detect lifting and venting. PRV must be designed for the correct flow and set pressure. Do not ignore the water vapor freight of biogas. Humid biogas under operational conditions can easily exceed 130% of the volume at reference conditions, especially in thermophilic fermentations or under dark gas domes. Passive vacuum relief valves do not protect a digester from air ingress caused by a gas consumer. They must be used as vacuum breaker on tanks with rigid roofs to protect the tanks from structural damage from vacuum. Use the active gas safety chain to prevent air ingress into the biogas plant and the formation of explosive atmospheres. That concludes the episode about pressure relief valves and the gas safety chain in the mini-series about the gas system of a biogas plant. I hope you learned something new, and I see you in the next episode of Biogas Basics.